Let's finish this semester up with our final chapter, which talks about induction and alternating current technologies. So this picture that we have here is a 3 millihenry inductor, and we will learn more about inductors here with our lecture videos for this week. So a changing magnetic flux induces a current and an EMF. So last chapter we talked about how a current can generate a magnetic field, but now we're going to talk about how a changing magnetic flux can induce a current and a voltage. And here we have a couple of examples of how this can happen. So in this picture here, we've got a magnet, a bar magnet, north poles facing up. We have a coil of wire here, and we move the magnet up through the coil, and that induces a current within this loop. Okay. And we pull the magnet back out of the coil, and that reverses momentarily the flow of the current direction. And we can see that here, the different directions in the current, depending on whether or not I was increasing the magnetic field through this loop or decreasing the magnetic field through this loop by moving the bar magnet toward or away from the loop. Okay. Now, if we flip the bar magnet, that induces current in the opposite direction. So now I flip my magnet, south is facing up, and I move that magnet toward the coil, and I induce a current in the opposite direction from the situation where I was doing the same thing before the north pole of the magnet. I pull that magnet back out, I induce a current in the opposite direction. If the magnetic field isn't changing through this loop by moving my bar magnet toward or away from the loop, then I don't induce a current. Okay, so this is what we call Faraday's law, and also a little bit of Lenz's law here too in action. So Faraday's law of magnetic induction says that an EMF, an electromotive force, can be induced if there is a changing magnetic flux. What is magnetic flux? So here we have an area in gold, and this and there's a magnetic field permeating this area. Here's our magnetic field vector, and the magnetic flux, represented by this capital Greek letter phi, is equal to the magnetic field, magnitude of the magnetic field, times the area through which we're evaluating the flux, times cosine theta. Theta is the angle between my magnetic field vector and a vector that would be perpendicular to our surface. Okay. So Faraday's law, this EMF, this electromotive force induced, is equal to minus the number of turns in a coil of wire, let's say, times the change in magnetic flux over time. Now, magnetic flux, so we just explained here, is related to the magnetic field and the area over which it exists. The unit of magnetic flux is 1 Weber, or sometimes that's also written as Tesla meter squared. Okay, so Lenz's law next. The minus sign here in Faraday's law is a result of something called Lenz's law. This indicates that the induced EMF creates a current and magnetic field that opposes the change in phi, opposite in direction, opposite of sign of the change in phi. Now, the important thing is that this induced magnetic field that we induce by the changing flux is always directed opposite of an increasing magnetic field and in the same direction as the decreasing magnetic field. Okay, so that's what this figure explains right here. Here I have a coil of wire, and I've got my bar magnet moving toward that coil of wire. Okay, the magnetic field from the bar magnet always leaves from the North Pole, so the magnetic field from the bar magnet is pointing to the right in this case. And as I bring that bar magnet toward my coil, I'm increasing the magnetic flux. So the magnetic field that I induce in the coil will want to oppose that increase in magnetic flux, and it will oppose the direction of the magnetic field that's coming toward it. So the induced magnetic field in the coil in this first situation is going to be toward the bar magnet, opposite the direction of the magnetic field coming out of the north end of this bar magnet. And then that induces a current here following our second right-hand rule. And so the thumb is in the direction of the current, fingers curl around in the direction of the magnetic field. So inside this coil of wire, this solenoid, the magnetic field is going to be pointing to the left. So I put my my fingers going through the magnetic coil will be pointing to the left. And so then that means that my thumb points in the direction of current, which would be kind of along these loops right here. Okay, and so then likewise, we can talk about the same situation for all of these four possibilities. The fourth possibility is discussed down here in these words, if you want to read through that. So for our scenario B, we had that bar magnet and we're moving it away from the coil. Okay, that is a decrease in magnetic flux, decreasing magnetic field. So when we have a decreasing magnetic field, the induced field will want to point in the same direction. So the field I induce inside the coil is going to be in the same direction as the magnetic field coming from the end of my bar magnet here. Okay, and then we flip the pole, and then but the same scenario still occurs. Okay. So here's an example of a problem to help us practice with Faraday's law. So we have a loop in a figure here that has an induced current of 100 milliamperes. The loop has a resistance of 0.83 ohms. What is the rate of change of the magnetic field in Tesla per second that created this induced current? We couldn't have this induced current if the magnetic field wasn't changing. So what is that rate of change of the magnetic field? And that's what we're going to find here. If the magnetic field we find to be decreasing, you're going to report your answer as positive. If the magnetic field is increasing, you're going to report your answer as negative. So we will see that the magnetic field, the rate of change of the magnetic field, dB dt, is decreasing. So we're going to report it as a positive answer.
All right, so we have a loop here, and it has a current in that loop that has been induced. What induced this current? A changing magnetic field, a rate of change of magnetic field. And so we're going to try to calculate what was that rate of change of the magnetic field in order to induce this 100 milliampere current within this loop here. Okay. So we have one loop, one turn of my loop. It has a total resistance, this wire here, of 0.83 ohms. Has a length of 10 centimeters, a height of 20 centimeters. So we know we've induced an EMF. We want to think about Faraday's law to help us with this. So our induced EMF is equal to minus the number of turns times the change in flux over the change in time. So here our number of turns is just going to be 1. And remember that change in, or magnetic flux is the magnetic field times the area of the loop times cosine theta. This is over delta t. Okay, so theta, that's the angle between the direction of my magnetic field and a vector that's perpendicular to the area of my loop. So my magnetic field, I've drawn it here as x's, so that magnetic field is pointing into the board. The B is into the board. Now a vector that would be perpendicular to my area, maybe that would be pointing out of the board towards you, but in any case, those vectors are parallel. B is parallel to the vector that's perpendicular to our area here. And so cosine of that angle is just going to be 1 if they're parallel. Okay. Now our magnetic field is changing, but our area of the loop is not changing. So we can write this as minus area times the change in B over the change in T. So it's this delta B over delta T that we're trying to solve for. Now, what do we do here with our EMF? Well, we know from Ohm's law that current, the EMF is equal to the current times the resistance. We know the current that has been induced. We know the resistance of our loop. So this left-hand side of the equation here, we can write that as the current that has been induced times the resistance of our loop. Okay, so now I'm going to solve this equation for delta B over delta T. delta B over delta T is equal to minus IR over A, then I can say that that's equal to minus 100 times 10 to the minus 3 amperes times 0.83 ohms, sorry about that, a little messy, divided by the area of my loop, which would be 0.1 meters times 0.2 meters. Okay, so then the rate of change of my magnetic field is going to be minus 4.15 Tesla per second. Okay, so our magnetic field, in order to generate this current, is decreasing. So if this is negative, that means that, if that's negative, that means that since delta B would be B final minus B initial, if it's negative, that means that our initial magnetic field must have been greater than our final magnetic field. Okay, so that means that our magnetic field is decreasing with time in order to generate this EMF. And so if our magnetic field is decreasing, we are going to actually input our answer as being positive when you stick it in to the answer section for this problem in Canvas. Okay, now also if I look back here at my equation for Faraday's law, I found that I'm going to have, if my rate of change of magnetic field is decreasing, that means that my rate of change of the magnetic flux is decreasing. So if this quantity is negative here, and then I have this minus sign out in here, this means that if I have a decreasing magnetic flux, then I have a positive EMF, which has been induced in my circuit.
And then we're going to practice with Faraday's law and Lenz's law. So here we have a circuit supplied with some EMF from a battery, and we have a resistor in our circuit, and this circuit lives inside a magnetic field. That magnetic field is going to increase from 0 Tesla to 0.2 Teslas in 3.5 milliseconds. And that's going to induce a current in our loop. So what is that current in our that runs through this resistor, which is the current that's going through our whole circuit? And if our current is counterclockwise, we're going to report a positive value. If our current is clockwise, we're going to report a negative value.
All right, so now we have a circuit inside a region of magnetic field that is pointing out of the board. That's what our dots here mean, pointing out of the board toward you. And this magnetic field is increasing. It's increasing from a value of 0 Teslas to 0.2 Teslas in 3.5 milliseconds. And so here's our circuit inside this magnetic field. We have a battery which is supplying 1.5 volts of EMF. The current is running clockwise, okay? And so there's going to be a current supplied by our battery, and then we have a resistor here with 10 ohms and of resistance, and we have the area of our loop would be 6 centimeters by 8 centimeters. Okay, so we want to find what is the current, the total current that is running through this circuit. So the total current that's going through this resistor here. Now, in order to find that, we actually have two currents that are operating in our circuit here. Okay. These two currents are from our two EMF sources in the problem. We have one EMF source, which is our battery, which is giving us a current around our loop from our battery. And we have an induced EMF because of this increasing magnetic field, which is inducing another current. So it's going to be the sum of those currents that's going to be the total current in our circuit. Okay. So easy, the current through the battery, the current from the battery in our circuit is going to be equal to the potential of our battery divided by the resistance of our resistor. And so then that's going to be 1.5 volts over 10 ohms. So the current being supplied to our circuit just from the battery is 0.15 amperes. Okay. Now the current that was induced by this increasing magnetic field, what is that? Okay, so again, that's going to be our induced current we'll see, induced, D-U-C-E-D, equals our induced EMF divided by the resistance. So our induced EMF, that's what we have to solve for, or that's what we have to find that to put it in here. So let's do that. Our induced EMF, for this quantity, I'm just going to think about the magnitude, the size of this induced EMF. So I'm just going to think about that and not worry about that minus sign, that minus in delta phi delta t. Okay, so the magnitude of our induced EMF is going to be n delta phi over delta t. So there's only one turn, only one loop here, so n is 1. And remember that our magnetic flux is magnetic field area cosine theta. The area of my loop is not changing. So this is going to be area times delta B cosine theta all over delta t. And remember, n was 1 here. Now our angle theta, that's the angle between the vector that's perpendicular to our area here of the wire and the magnetic field vector. And these are both parallel to each other. So cosine of theta here is just going to be 1. So our magnetic field is increasing from 0.2 from 0 teslas to 0.2 teslas. And so our EMF here is going to be the area of our loop, which will be 0.06 meters, its length times its width, times 0.08 meters, times the change in magnetic field, so 0.2 Tesla minus 0 Tesla, all over the time over which this happens, and that's 3.5 milliseconds, so 3.5 times 10 to the minus 3 seconds. So my magnitude of my induced EMF is just 0.274 volts. Okay, so if I take that up here to my equation for my induced current, I've got 0.274 volts of EMF divided by 10 ohms. So my induced current is going to be 0.0274 amperes. Okay. So I've got the current from my battery, the induced current from the fact that the magnetic field is increasing over time. So we have a changing magnetic flux per time. Okay, so we want to think about how are these currents going to add or subtract from each other. Now we need to think about what direction is our induced current moving around our loop. We know that the current from our power source is rotating clockwise here. As we think about the direction of the conventional current will move from the negative to positive end of my terminal. So that direction of the conventional current from the battery is going to be moving in the clockwise direction. So for the induced current, what direction is that coming? What direction will that be? So by Lenz's law, remember Lenz's law, since our magnetic field here is pointing out of the page and it is increasing, then the induced magnetic field will be opposite of that direction. So my induced magnetic field, which I'll write here with my red marker here, B induced, will be pointing into the board here. So my induced magnetic field will be into the board here. So what does that mean for my induced current? Okay, so I'm going to think about my second right-hand rule. So everywhere along this loop, my fingers, remember for our second right-hand rule, my thumb points in the direction of current, fingers curl in the direction of the magnetic field. So if anywhere along my loop here, the magnetic field that's been induced inside the loop points inward into the board inside here. So let's just pick this length of my wire here. I take my fingers and I try to curl them into the board. That means that my thumb here has to point in this direction for current. Okay. And then if I come up here, fingers have to go into the board. My thumb is in the direction of current. So here, I has to be pointing upward, and I can do this all the way around. And so that means that the direction of my induced current is also the same as the direction of the current coming from my battery. So for the total current in my loop, I'm going to sum up my current from my battery plus the current that's been induced by our increasing magnetic field, And so if I add up my 0.15 amperes plus my 0.0274 amperes, then the total current is going to be 0.1774 amperes, and it's going to be moving in this clockwise direction. Now let's say that your magnetic field was instead decreasing. Okay, then your induced current would be moving in the opposite direction of the current that is supplied by the battery. And so then the total current would be the difference of the current in your battery and the current that was induced, because the induced current would be moving opposite the direction of the current from your battery.